Hello, welcome back. In this video, you'll see how the derivation of the stiffness matrix for the truss element is derived. Okay, in the previous video, we have seen that the relationship between local coordinate system and global coordinate system, where q1 dash it is the displacement of the node 1 and node 2 in the local coordinate system. Q it is the displacement of the node 1 and 2 in terms of global coordinate system, that is q1, q2, q3, q4, where q2 are the displacement of the node 1 in the x direction and y direction, and q3 and q4 are the displacement of the node 2 in the x direction and y direction. It is in terms of global coordinate system. Okay, this L, it is nothing but a transformation matrix, that it builds the relationship between local coordinate system and the global coordinate system. Okay, let us derive the stiffness matrix for the truss element. Already we have derived the stiffness matrix for the bar element. What is the stiffness matrix for the bar element? K is equal to AE by L 1 minus 1 minus 1 1. Okay, where stiffness matrix of the bar element AE by L 1 minus 1 minus 1 1, it is derived by using the strain energy. In the strain energy, we have taken half of integration of sigma t epsilon into dV. What is sigma here? Transpose of the stress. Epsilon is equal to BQ, where B is the strain displacement matrix. It is already done in the class. Epsilon is equal to BQ. Okay, by using the relationship between strain and stress, we can say that sigma is equal to EBQ. Okay, just substituting all the relations, sigma is equal to EBQ and epsilon is equal to BQ. As bar it is for one dimension, it can be written as A into dx. Okay, dx it is in terms of global coordinate system. The same thing it is written in terms of local coordinate system. Okay, when it is compared with this equation, we can say that K is equal to A by L 1 minus 1 minus 1 1. It is stiffness matrix for the bar element. It is done in the class. Okay, in the similar way, strain energy is equal to the same equation it is used, but the only thing for the truss element we are using the transformation matrix. What is Q here? Q it is nothing but L into Q in terms of global coordinate system, where Q it is defined in terms of global coordinate system. The same thing it is substituted here. Q is equal to LQ. Okay, Q it is LQ. So when it is compared with this equation, when the displacement values are removed, then it will be stiffness matrix. Okay, when the displacement terms are removed, Q when it is removed, then what you will get, that is the stiffness matrix for the truss element. So K is equal to LT K into L. What is L? L is the transformation matrix. Okay, it is already derived in the last video. L is equal to LM0000 LM. What is LM here? It is are the direction cosines. L is equal to cos theta, M is equal to sin theta. I will show you here. Okay, see here, this is the truss element. It is node 1 x1 y1 coordinate and node 2 the coordinates are x2 y2. So what is the horizontal dimension? It is x2 x1. Vertical dimension it is y2 minus y1. What is cos theta here? Adjacent side divided by hypotenuse. Hypotenuse it is nothing but the length of the element. So cos theta is equal to x2 minus x1 by LE. Sin theta is opposite side it is y2 minus y1 divided by hypotenuse, that is the length of the element. Sin theta is equal to y2 minus y1 divided by LE. Okay, using all these coordinates, we can say that LE is equal to, by hypotenuse theory, it can be said as square root of x2 minus x1 whole square plus y2 minus y1 square. Okay, now Stiffness matrix Ke is equal to LT KL. What is L here? It is transformation matrix. How this transposition come? It is by this strain energy equation. Removing all the displacement values, we will get this stiffness matrix. Okay, L, it is the transformation matrix. Okay, what is transpose? You are changing rows into columns, column into rows. Okay, this is transformation matrix. Transpose of this one, it is the transpose of the transpose of the transformation matrix. So rows are changed to columns, columns are changed to rows. So this is the transpose. Okay, substituting all the values, LT is the transpose of transpose matrix, and K is the AE by L 1 minus 1 minus 1 1. We are using for the bar element, stiffness matrix of the bar element. Okay, substituting all these things, LT it is the transpose matrix, K is AE by L 1 minus 1 minus 1 1, and L is the transposition matrix. Okay, multiplying all this, you will get finally this equation. This is the stiffness matrix for the bar element, EA by L, L square LM. Okay, see here, you just observe this 2 by 2 matrix, L square LM LM M square. Okay, the same 4 elements are repeated here, only thing with the negative sign. Okay, the same 4 elements are written here, minus L square minus LM minus LM minus, the 4 elements are written here, the same 4 elements are written here. Okay, it is repeating. What is here? Young's modulus of the truss member. A is the area of the truss member, L is the length of the element. This is the stiffness matrix for the truss element. What is L and M here? L and M are the direction cosines. L is cos theta and M is sin theta. Okay, let us see what is the, how to derive this stress in the element. We already know that sigma is the stress, it is EBQ, but for the truss element Q, it is LQ. It is in terms of local coordinate system. We are writing the same thing in terms of global coordinate system, EBQ, where Q it is written as LQ. What is L? It is the transformation matrix. What is Q? In terms of global coordinate system, it is Q1, Q2, Q3, Q4. The same thing substituted here. Okay, we already know that B is equal to 1 by LE minus 1 1. E is written as E only. B is 1 by LE minus 1 1. Okay, what is L here? LM 0 0. It is the transformation matrix. And what is Q? It is the displacement values. Okay, simplifying this, this is the stress equation for the truss member. Okay, so this is the stress in the truss element. And this is the stiffness matrix for the truss element, EA by LE, L square LM LM M square. The 4 same values are repeated here with the negative sign. The same 4 elements here, the same 4 elements here with the positive values. Okay, thank you.